In this video, we're going to take a look at projections of vectors, and we'll see how we can apply the dot product and some other vector techniques to find projections and apply them. So let's get into it. So first of all, we've learned that the dot product of two vectors, u and v, comes from multiplying their first components, u1 and v1, and their second components, and then adding those products. And we've also learned that this can be used to find an angle between two vectors and see if they're perpendicular or not. Well, now we're going to see another application here. We're going to talk about projections. A projection of a vector is this. If we have one vector here, let's say this is u, and then we have another vector that looks something like this, going off in another direction. That's v. Well, if we want to project v onto u, we need to travel at 90 degrees from v down to u. So let's see if we can do that. So we're from the head of v, from the arrow, we're going to go straight down to u. And we find this point right here. And graphically, that represents the projection of v onto u. So it should be right on top here. So this yellow vector right here, this yellow vector is the projection of v onto u. Okay? And when we think about forces and things like that, that's the amount of force going in this direction. Well, let's see, do some examples and see how that works. So again, this formula comes from u dot v all over the magnitude of v squared times the vector v. Okay? Now notice this is a scalar times a vector. So this is just going to give us a stretch or a shrink of that particular vector, v. So let's see here. Here we have two vectors, u and v. Let's start out by finding the dot product, u dot v. We multiply the first terms, 3 times 6, and the second components, 4 times 0. And that gives us 18. Well, let's just go and do it. It gives us 22. No, sorry about that. 4 times 0 is 0. How about 18? All right. And then we have the magnitude of v squared. Well, that's just going to square the first component, square the second component, and add it. And the square here, normally when we find the magnitude, we take the square root. But in this case, since we're squared, we don't need that square root. And that's going to come out to be 36. So we have the projection of u onto v is 1836 dot v, which the vector v is 6, 0. Okay? And so this is 1/2 times 6, 0, which is 3, 0. All right? So let's go ahead and graph these and see what we got. Let's start with u. U is 3, 4. So we're going to go 3, 4, find our endpoint here, and draw a careful vector there. And then we have v is at 6, 0. So let's graph that one here. Over here, oops. Find our endpoint. From the origin and standard position, we have 6, 0. Then we want the projection. Well, the projection here is 3, 0. So 3, 0 is right here. And we see that that is just dropping 90 degrees down from u. Once again, this was, let's see, this was u. This is v. And this is our projection vector p here. Okay. All right, let's try another one. We have All right, in this one, we're going to find P dot Q, and that gives us, when we multiply, -2 times -6 plus 4 times 1, which is going to give us, there's a negative there, 12 and 4, that's 16. And then we have the magnitude of Q. We're going to project P onto Q here, squared. And that's going to give us -6 squared plus 1 squared, which is 37. And so our projection of P onto Q is 16/37 times Q, which is -6, 1. In decimal form, this is -2.6 and 0.4. Okay. So let's go ahead and graph these and see what it looks like. We have our first one, P, -2, 4. And -2, 4 is going to be down up here. And we'll call that P. We better come back here and call this our projection, okay, of U onto V. All right, so we have P, we have Q. Q is at -6, +1 right here. And freehand in this, so there we go. And then we have our projection vector, -2.64, and -2.64 is going to end up, 0.4, sorry, -2.6.4. Well, that's right about over here. Okay, and so right about there. And we can check and we can say, does that look pretty orthogonal there? Right angle? It sure does. So this vector right here, this green vector, that's our projection of P onto Q. That's how it works. Okay? So we see, how does the projection vector relate to the first one? Well, it's on the first vector, it's just shrunk, or sometimes it's actually extended. And so it's always going to be in the same direction, either shorter than the original vector or longer. All right, let's look at a little application here of these projections. Here we have a 50-pound force F that's making an angle of 40 degrees with the horizontal. All right, so this is our vector F right here. Okay, and it's pulling up on a box, up a plane. The inclined plane is at 15-degree angle with the horizontal. We want to know what is the magnitude of the effective force that's pulling the box up the plane. All right? So you can think of it, we got some rope or somebody pulling up at an angle on this box as we're trying to move this box upward on the plane. Okay? So the important thing to understand here is that effective force means what is the force if we pull up. Let me kind of redraw this a little bit. If we pull up at this angle 40 degrees with the horizontal, what is that force that's going in the direction of this plane? This plane is going up at 15 degrees. So how much of this force is actually pulling up? Some of the force is lifting the box off the plane, off this ramp, if you want to think of it that way. Some of the force is dragging it up. So we want to find that much. Well, first thing we need to find is we need to find this angle right here. Okay, and this angle right here, we might call that right there, we might call that theta. If I can squeeze that in there. Okay, and so the first thing we need to realize is that theta is going to come from this 40 degrees, because That's 40 degrees, the force vector is off of the horizontal. But this is 15 degrees, so we got to take away 15 degrees, because when we put it together, if we draw a parallel line here, that line's parallel to the ramp roughly. Okay, and so there's a little 15-degree angle, so we got to take 15 away from 40, and that's going to leave us with our theta. And so theta is 40 minus 15, which is 25 degrees. All right, so we have 25 degrees, and we need to realize what we're finding is the projection. We're finding the projection vector that's going down here. So if we draw this 90-degree angle right here, we want to find how much of this angled F vector is going in the correct direction there. And so what we have is we have this triangle, looks like this. I'm going to kind of blow it up a little bit. We've got our theta, which is 25 degrees, and I've kind of flattened this triangle out so we can see it better. And we know that this force vector F is 50 pounds. Remember, the length of the vector is the magnitude, and vice versa. We want to find out this, we'll call it P. That's our projection vector. Okay, how much of that force is going up the ramp there? Well, we can see this is just a cosine situation. We know the cosine of 25 is P over 50. If we multiply both sides by 50, we get P, flipping around here, is 50 times the cosine of 25. And that comes out to be about 45 pounds. And that makes sense. It should be a little less because, like we said, some of the force is lifting the box off the ramp, and some of the force is pulling up the ramp. All right, let's look at one more situation. If we take this a step further, we have something called work. And in physics, work is the force applied over a certain distance. All right, you can think of it this way. If we're dragging this box and we just drag it 1 inch, that doesn't take a lot of work. Okay, but if we have to drag this box 20 feet up a big ramp, if it's a heavy box, that takes more work, more effort in a sense. So that's the definition, a force over a distance. We define it like this. We can have the force, the magnitude of the force times the magnitude of the angle vector, okay, times the cosine of theta, okay? Or, if we know the vectors in component form, we can use this dot product, and that work is a dot product of the force and the direction vector. AB is a direction vector. So, let's see. Let's try this. Let's go back to our box, and we want to consider the box as being pulled 50 feet up. The force F, that makes an angle of 25 degrees with the inclined plane. Find the work done by the box. So here's what we want to do. If it's pulled along this vector from point A to B. Okay, we want to find the work done by that force. Well, we know it's a 50-pound force. We can go a couple ways. We could either find the magnitude of this, and we know the angle is 25 degrees, and then we could use the first one. Or we could find a vector for F. Okay, well, let's go with the first one here to start. We have the magnitude of AB is square root of negative 6.2 squared plus 23.2 squared. And so this gives us a magnitude of 24.01. We'll round off there, that's good. And so our work is going to be the magnitude of F, our force, times the magnitude of AB, times the cosine of the angle. And in this case, we have our force is 50 times 24 times the angle between them, which is 25. Actually, the cosine of the angle between them. Cosine of 25. And that's going to give us approximately 1087.5, so we'll round off to 88 foot-pounds. Okay, that'll work. Real quickly, the alternate way to go about this is to find our force vector. Our force vector is being pulled up at 40 degrees, and so we can say that this is 40 degrees times with our magnitude of 50, so that would give us F being 50 cosine of 40 and 50 sine of 40. Actually, we'd have to use the 25 here. Let's go ahead and use the 25 because that's in relation to our angle that we're going. Actually, we've got to make one more little correction, maybe two actually. See a little problem in this error in this problem here. We've got if this is we're going off in this direction here, and if we consider this to be negative, positive, that's going up to the left because we're talking about this. We need our directional vector here. So let's take real quickly, see if we can fix this up one more time. So our directional vector is going off in a 140 degree angle because it's going up to the left, 140. That's going to be a vector there. And these actually got swapped around, which didn't matter for our first method. And what that would give us would be, we should be going farther left. So this really should be 23.2 here. A typo. 23.2 negative and 6.2. So a little error in the problem there. Okay, and so what that's going to do is if we do this, if we take f, which is 50 cosine of 140 and 50 sine 140, and you do the dot product with negative 23.2 and 6.2, you see that's going to give us this direction vector that's going off left and up at a 15 degree angle. And so if we do the dot product of those vectors there, we will get our 1088 number. I'll let you try that out. And that's foot-pounds again. All right, so there we have it. Two ways to get work, and we can see how we can use the dot product and work here. We can use the projection to find the amount of force in a certain direction. And we saw that a projection is just a line that is 90 degrees from the arrow end of a vector towards another one. So it's the amount of a vector going in a certain direction. All right, there it is. Good luck.